start with the ILP, write the LP relaxation, and then you round. So in the rounding, what we have done is the following. Pick each set with probability x sub s and add to T sub I, right. Return the union of these sets. Yeah? And what we saw was, one, the probability that T is a set cover is at least 1 minus 1 over n, right. So n is the size of the set, right. This part is clear, but the probability of picking that the set we return is a set cover is at least 1 minus 1 over n. So what we are what we are left to do is to prove that size of T is at most alpha times opt for some alpha, right. So theorem, a size of T is at most some O of log n times opt, okay. And the proof is the following. The size of a set in one round, this is equal to the expected size of the set. So all of this is an expectation. So the expected size of a set in one round is just sigma x sub s, right, because you interpreted the variable x sub s as the probability of picking the set. Then the expected size of the set you return in one round for particular I is sigma x sub s, right. This is by linearity of expectation, but this quantity, the sum over x sub s, is actually the optimal solution of the LP, right. That is the objective function. The objective function was sum over sigma x sub s. Therefore, in each round, the expected size of the set you choose is of size at most opt of the LP, which is at most opt. Because the LP gives you a lower bound. Therefore, the expected size of T is equal to, so is at most, since T, how many rounds do we do? 2 log n rounds. So is at most, let's say 2 log n times opt LP, which is at most 2 log n, 2 log n times opt. Okay, so we have a log n approximation. So the approximation factor gets worse as n goes to infinity. As the size of your set, ground set, grows larger and larger, the approximation factor that your algorithm is guaranteeing gets worse and worse. And this is different from the vertex cover problem, where no matter how large the graph is, you know the vertex cover solution is at most twice the optimal. So here you are only doing something weaker than what is possible for vertex cover in the set cover problem, right. And let me just mention it here. So the theorem, I think Feige in around 98, and before that I think Feige in 02, something like this. So around roughly late 90s, early 2000s could prove that better than a C log n approximation for set cover would imply P not equals NP. Okay. So, I am cheating a little bit, but Feige's result was on a slightly weaker complexity conjecture, but for all practical purposes you cannot do better than log n unless P equals NP or something like that happens. Okay. So, in fact, this is the best algorithm, the best approximation factor one can guarantee. Yeah. So, you can improve on the constant factor, the lower order terms, but this is essentially what you can do. Okay. And just like vertex cover, where we saw a simple combinatorial algorithm, for set cover as well, there is a simple combinatorial algorithm. Just greedily choose the set that covers the maximum number of remaining uncovered elements. And you can show that there is also a log n approximation, but I will not do it here. Okay. No, you get the same bound about log n, but the algorithm is simpler. The algorithm is just a greedy algorithm. Each time pick a set that covers the maximum number of yet uncovered elements. And that gives you also gives you a log n approximation. So you don't have to solve the linear program. It's a combinatorial algorithm. But the approximation factor remains the same. So what is our plan? Our plan is to look at set cover in a geometric setting. So for general set systems, if you have points and arbitrary sets, then you cannot do better than log n. So our question is, if the sets come from geometry, right? So for example, you might have these points might be users, and the disks may correspond to the transmission range of some radio towers, and maybe you want to only switch on the smallest number of radio towers so that every user still has signal, every user is still covered. Okay. So in this case, the elements of the set are points in the plane, some set of points in the plane, and the sets are disks. So you want to pick the smallest number of disks that cover all the points. Okay. So one example is, of course, in antennas and radio stations and towers. The set cover problem also shows up in many scheduling problems. Geometric set cover shows up in many scheduling problems. I will not be able to tell you why or how, but it shows up in many. So there are many applications beyond just geometry. Okay. So we want to develop tools to get a better approximation than what is possible for general sets. That's going to be our goal. Okay. In order to do that, what we are going to do is to introduce a seemingly unrelated problem. Okay. So these are called, this is called the Epsilon Net problem. This is a combinatorial problem. We will relate it to solving set cover later on towards the end of the lecture. So what is an epsilon net? Oh, so let me do this. So before I do epsilon nets, let me just tell you one more thing. So if you're given a set system, yeah, we can define a dual set system where, let's call it H star, where the elements of H star are the sets and the sets correspond to the points. Okay, what does this mean? I'll just oh, I see. Let me just, this is S. This is S. Yeah. So So let's take this example on the left. So let's give these points 1, 2, 3, 4, 5, 6, 7, and the sets, let's give them names A, B, C, and D. So if this is the set system, then the dual set system, in the dual set system, the elements become the disks, right? So the elements become the disks. So H star consists of the disks A, B, C, and D, and the sets correspond to, for every point, the collection of sets that it contains. So 1 is only in set A. Yeah, this is the set corresponding to 1. The set corresponding to 2. So 2 is in the disk C and the disk B. So this is B comma C. Then let's look at something else. 6 is in D and C. So this is corresponding to 2, and so on, right? So this is the dual set system where the sets become points and the points become sets. This is also a set system, right? So points and sets.
So here only what is X is the set of points.
X is the set of points in the original set system or the primal set system. Here, yes. Here X is 1 to 7. S are the sets A, B, C, D. The disks A, B, C, D. In the dual set system, the elements are the sets A, B, C, D, and the sets are for every point the set of the collection of sets that cover it. Okay, so now I can define what is called the hitting set problem. Pick Y subset of X of smallest size such that for every S in S, Y intersection S is non-empty, which means that you again look at the primal set system. I want to pick the fewest number of points, fewest number of elements among 1 to 7, so that if I look at any disk, at least one point is chosen. So I could have chosen 6. 6 hits C and D. Let me use something else. So 6 hits C and D. 1 hits A. 3 hits B. So 1, 3, and 6 form a hitting set for this set system, right? It's a set of points I want to pick so that for every set, at least one point is chosen. This is the same as the set cover problem in the dual set system. Is that clear? In the dual, so I'm defining a new problem, a seemingly new problem called hitting set. In the hitting set problem, what do you want to do? You want to pick the minimum number of points so that if I look at any set, there is at least one point chosen. In the set cover problem, I want to pick the smallest number of sets so that if I look at any if I look at any point, there is at least one set covering it. When you look at the dual, their roles have changed. So the hitting set problem in the primal set system or the original set system becomes the set cover problem in the dual set system. So while I'm calling it the hitting set problem, it's really just a set cover problem. Yeah? Does that make sense? Okay. The reason to do this, so if you have an abstract set system and you want to solve hitting set, well, just take the dual and solve the set cover there and use the same machinery. Okay? So you would get a log of the number of sets approximation. Okay. Now we can do epsilon nets. The reason I wanted to introduce hitting set is that I'm going to describe epsilon nets in the language of hitting sets as picking points instead of picking sets. But because of duality, they are the same thing. Okay? So it's just easier to describe it in terms of points. So given a set system, size of X is n, the set S in S is large if size of S is at least epsilon n. Okay, a set is said to be large if it contains at least epsilon n points for some epsilon positive. Okay, so you only want, so let's say epsilon is half. You only want to look at sets. A set is large if it contains at least half the points of your set system. Right? A set Y subset of X is an epsilon net if Y intersection S is non-empty for every S that is large. So I don't want a hitting set for the set system. I only want to pick a small subset of points that hit all sets that are large, and large is defined by epsilon. Okay. So if epsilon is 1/10, I just want to hit all the sets whose size is at least 1/10 of all the points, and all the sets that contain at least 1/10 of all the points. Okay. So that's an epsilon net. So let's take an example. So by the way, we don't have to assume that the set S, okay, so in general, okay, so you don't have to assume that the set system is finite. Okay, so these definitions also work for infinite set systems, in which case you only want to hit all sets whose measure is at least something. Okay, so but let's just work with finite set systems. So all of these results will extend it to that setting. So let's look at points. Let's look at points on a line. These are the sets. The sets X are the points, let's say 1 to n. And the sets are defined by intervals. Okay. So this is a geometric set system in one dimension. The elements are points on the line and the sets are intervals. Okay. And I want to construct an epsilon net. I want to pick a small subset of points so that if I look at any interval of length at least epsilon 1 over epsilon, at least epsilon n containing at least epsilon n points, then one of the points is chosen. So how many points do you need? So our question is going to be how large should Y be? So we are not asking anymore how to compute the epsilon net. We are not asking for approximation algorithms to compute an epsilon net of small s size, but our question is really combinatorial. We just want to know how large should Y be. So in this case, if you have points on a line, and the intervals being the sets being intervals, how large should Y be? Sure, you could pick all the points. That's an epsilon net, but you could do better than that, right? You only want to hit intervals that contain at least epsilon n points. N by 2, okay, you could pick every alternate point. And that is an epsilon, that's also an epsilon net, but you could do better. So I give you an epsilon, and you have to tell me how large an epsilon net should be. It should be a function of epsilon, of course. One by epsilon. Why? You want to hit all the sets of size at least epsilon. All the intervals, in this case, all the intervals of length at least. Yeah, so what are you doing? So if you pick every, so here in this case, you can also give a constructive argument that, yeah, pick every 1 over epsilonth point, right? Right. So pick every 1 over epsilonth point. Okay. And this is an epsilon net. Right. So this has set. So then size of y is ceiling 1 over epsilon. So I am going to ignore these floors and ceilings and be a bit sloppy and just say the size of y is O of 1 over epsilon. So pick every one. If you want to hit all intervals of length 10 containing at least 1/10 of the points, pick every. Yeah, that's it. That's an epsilon. The important point is that why does this move? The size of the epsilon net is independent of n. The size of the epsilon net in this case does not depend on the number of points, right? It's a constant size set. For a fixed, if epsilon is a constant, then the size y, then set y has size constant, and if you look at any interval of length at least epsilon n, then one of the points is hit. Okay, good. That's easy. Let's look at another example. So now your set system X is a subset in the plane, the size of X is equal to n, and the sets are half spaces in R2. Okay, so you have a bunch of points. This is your set X, and the sets are half spaces. So what do you want to do is that a half space is large if it contains at least epsilon n points on its side. Yeah. Now you want to pick points so that if you look at any half space that contains at least epsilon n points, one of your elements you have chosen is in that half space. It hits every half space that has size at least epsilon n. Okay? So our question is, how large should y be? So again, y is subset of X such that y intersection H is non-empty for all H such that size of H is at least epsilon. So I could choose any half space and look at all the points, and there must be one point of y that I can see as long as the half space is large. It contains at least epsilon n points. and you can immediately see applications, right? For example, if you have points in the plane and you have a query and I want to know if there are any points in your input set that are in the half space, and I want to build a data structure, but your data structure can make mistakes, right? So if you have a million points and your half space contains 1 point, then you can say, okay, yeah, it doesn't contain any point. You're okay with that, right? But if it does not lie, if the half space contains many points, then your data structure does not make a mistake. It says, yes, there is a point. And so you can immediately see that you can build a data structure that approximately answers queries that says, whether a half space contains a point or not, at least for large half spaces. So what would you do in this case? So on an interval, you picked every 1 over nth, 1 over epsilonth point. Choose an area of epsilon boxes. That will be too many boxes. No, a half space is defined by a line and everything on one side of a line. We want to pick an epsilon, we want to find an epsilon net for this set system, which means if I give you points and half spaces, I give you a set of points, so that, and you want to pick a subset of these points, so that if I look at any half space that contains at least epsilon n points, then one of your chosen points must be in your set. No, for every line. I want to pick a set Y or a subset of X such that for every half space containing at least epsilon n points, Y intersection the half space is non-empty. The question is, how large should Y be? So you've seen a lot of geometric objects, and what in the morning you saw something. Convex hull, right? So if you have points, the natural thing with half space queries should with half spaces, I don't know why this keeps moving, with half spaces should be if the half space contains a point, it must intersect the convex hull of the points, right? You construct the convex hull. The convex hull cannot contain a point without intersecting the half space. The half space cannot contain a point without intersecting the convex hull. Yeah, okay, fine. So the convex hull seems like a reasonable thing to build. Fine. So you have a convex hull, but we are not interested in we are not interested in half spaces like this that contain 1 point. The thing should chop off a large fraction. No, for a fixed epsilon. Assume epsilon to be fixed. If you like, choose epsilon to be 1/10. For every epsilon, you build an epsilon net. So if you change epsilon, then you build a new epsilon net. Okay? So that could be n. The points could be in convex position. Okay, so here is the idea, and why is it scrolling? Okay. So here are the points. Okay. So let's say this is the convex hull. The idea is the following. Choose an arbitrary point on the convex hull. Yeah. Let's say this is the point P that you've chosen. Okay. Now I'm going to radially sweep, and the convex hull is to few points. Let me just add a few more points. Okay. Okay. I'm going to radially create these wedges from P, so that each of them, each wedge contains how many points? So if you like, epsilon n minus 1 points. I'm assuming epsilon n, here it should be ceiling epsilon n minus 1, but okay. So from P, I radially create these rays. I sweep along, and at the moment I have ceiling epsilon n minus 1 points. I create a ray. So I've partitioned the point set into how many groups? So we have partitioned the points into about 1 over epsilon groups. Okay. Now let's look at a half space that contains epsilon n points. So claim any half space containing at least epsilon n points must do what? Each wedge has less than 1 over epsilon points. Less than epsilon n points, strictly less than epsilon n points. And half space is large if it contains at least epsilon n points. So what should it do? It should intersect at least 2 wedges. Each wedge contains less than epsilon n points. A half space is large if it contains at least epsilon n points. Therefore, every half space that is large must intersect at least 2 of these wedges. Right? You cannot have a half space that looks like this, that is large, containing only all these points on this side, because this set only contains 1 over epsilon points. Less than epsilon n points. Right? Not necessary. The rays. No. All I'm saying is that if you look at any half space that is large, that contains epsilon n points, more than epsilon points, it must intersect at least two of these wedges. It cannot intersect just one, right? It contains points from both, from at least two wedges. So it can look like this. So it contains some points from here and some points from here, right? It cannot look like this where it contains only points below this, because there are not enough points. Yeah. Here. Yeah, but that they will intersect on the convex hull, but they may not intersect at a point on the convex hull, at a vertex on the convex hull. Okay. So now I claim that if you pick for every wedge, every red ray that you've picked, if you pick the two ends of the convex hull, let me choose another color. Let's pick the two ends of the convex hull for each of these rays. Then the number of points you have chosen is about 2 over epsilon, right? This is the set Y. Okay, and I claim that, yeah. Okay, let's do this again. So you picked a point and you sort of radially sorted the points so that in every partition has less than epsilon n points. A half space is large if it contains at least epsilon n points. So every half space must contain points from two partitions, right? So there must contain points from two partitions. So I claim that if it contains points from two partitions, it must intersect the convex hull of this. This is the convex set, so it must intersect the convex hull of that partition, of the points in that partition. So therefore, if I take for every red ray that is from P, I take the two endpoints of the convex hull intersecting that ray. Those points I claim form an epsilon net, because every such half space that is large must intersect two of the wedges and therefore must contain one of those endpoints of the convex hull. Okay, but almost, because you might have a half space that contains P, but I also choose P in the convex set. Right? So you have a epsilon net of size 1 over epsilon. Okay? Okay. So here is another example, but I will not So the reason to take 2 is you don't know on which side of the half space the point lies. So that's why you take both of them intersecting this. So imagine rectangles sitting on the x-axis and points, and the claim is that there exist epsilon nets of size 1 over epsilon. I'm not going to prove this. I'll upload notes which you can look at, which has solution. Okay. Okay. So, I mean, as you can see, from intervals already to half spaces, you needed clever ideas. And now, if you have these three-sided rectangles, you need slightly more clever ideas. And now, if you have disks, it becomes harder, right? So these techniques that we just saw do not generalize to more complex set systems. So what we are going to do is to look at a completely different way of constructing epsilon nets that involve random sampling. Okay. Again, let's go back to the case of intervals. So you have points on the line. So all we are doing is just sampling each point from X with probability P. We will determine what P should be later, but we just sample these points. So you get some set. Okay, and we would like to find P so that this is an epsilon net with good probability. Okay, so we will show that for a suitable P, S is an epsilon net. S is an epsilon net, not with hyper, and the size of set, the size of the set S, size of the epsilon net, is independent of n as we want. Okay. Okay. So the idea is now we've thrown out all these complicated combinatorial arguments and said let's just sample points with probability P, and this should be an epsilon net if you sample with the right probability. Okay. So let's look at the situation. Okay. So when does S fail to be an epsilon net? S fails to be an epsilon net if there are these two consecutive points that you picked in S, but then you somehow did not pick these epsilon n points that lie in between them. Right? That's when S. If there are 2 points of S consecutive, so that between them there are epsilon n points that you've not chosen, then S fails to be an epsilon net. Okay. So let's call such an interval defined by 2 chosen points of S with epsilon n points in between unchosen as a canonical interval. Okay, so canonical interval is an interval which is defined by 2 points in S, 2 consecutive points in S with epsilon n points in between. Okay, so let's compute the probability of obtaining a canonical interval. So what is the probability of getting a canonical interval that is defined by 2 points, which means those 2 points are in S and now everything in between are not in S. Right? This is P square, that the 2 endpoints are chosen, times Sorry. Okay. So the number of, so let me just quickly do this is p square e to the minus p epsilon n. So the number of canonical intervals is n square. You lose bound. Canonical interval is defined by 2 points, so it's at most n square. Okay? Because every canonical interval is defined by 2 points. I'm using a weaker loose bound here, but that should be sufficient. Right? So the expected number of canonical intervals is at most n square p square e to the minus p epsilon n, right? Okay. So this is the expected number of canonical intervals. So now choose p to be some constant over epsilon log 1 over epsilon. Okay. Then this quantity is strictly less than 1. Okay. This is a calculation you can do and check that if p is 1 over epsilon log 1 over epsilon times some constant, then the expected number of canonical intervals is smaller than 1. Okay, this quantity becomes smaller than 1. Okay, so you can check quickly n square c square over p epsilon n. Yes, epsilon square n square log 1 over epsilon square e to the minus epsilon n. Right. So the n square gets cancelled, epsilon n gets cancelled, and you get something that is smaller than 1. Okay, so if the expected number of intervals is smaller than 1, then there is an epsilon net with no canonical intervals, which means that it is an epsilon net. Okay. Since the expectation is less than 1, this implies there exists a set S such that there are no canonical intervals, which implies S is an epsilon net. And what is this expected size of S? This is n times p, right? Which is n times p is c over epsilon n log 1 over epsilon, right? So this is O of 1 over epsilon log 1 over epsilon. This is worse than what we started with, because for intervals we saw there is an epsilon net of size 1 over epsilon. But here we have an epsilon net of size 1 over epsilon log 1 over epsilon, but still independent of n. Okay. The reason to do this is that now the random sampling idea will generalize to other set systems. Okay. So So let's construct, let's look at another example. The set system is points and disks. So you want to hit every disk that contains at least epsilon n points. Okay, and I will just give you the idea. So a canonical disk is defined by 3 points. So this doesn't look very much like a disk, so let me draw it. Right? In this case, a canonical disk is defined by 3 points, and every disk containing a, so claim every disk containing at least epsilon n points is contained in the union of 2 canonical disks. Okay. Therefore, if we compute an epsilon over 2 net so every disk containing epsilon n points is contained in the union of 2 canonical disks. The canonical disks are defined by 3 input points. So you can think about it. Basically, you start with a disk that does not contain points on the boundary. You can grow it until it hits a point, then you can move it till it hits a second point, and now you can sort of construct a canonical disk by moving perpendicular to this line segment, and perpendicular in the other direction, and take 2 canonical disks that contain 3 points on the boundary, and every such disk is contained in the union of 2. I am hand waving here, and this you can do we will do in the tutorial. Okay. And now the idea is the same. Choose points with probability p equal to c over epsilon n log 1 over epsilon, and this is an epsilon net. There is and you can prove that there is an epsilon net of this, of size 1 over epsilon log 1 over epsilon. Okay. So I don't have the time to do this, but it's in the notes and I'm going to share it with you. So what is really going on is that this canonical, now let's try to abstract it. The canonical disk is defined by 3 points. The canonical interval is defined by 2 points. Now if a canonical object can be defined by d points for some d, then this whole machinery should generalize. Okay. So in fact, what is weaker than what we require is the following. So what we require is that if an object is defined by d points, canonical object is defined by d points, then we can construct an epsilon net by just random sampling. Exactly the same argument. And so in fact, you can do something weaker. All we want is that, so given the set system and y subset of x, the set is y subset of x, y restricted to s or s restricted to y, is the set of all sets the collection of sets that are defined if you just look at some subset of x. So if you look at only these points that are a subset of the entire point set, then you might get sets like that. And if you restrict yourself to just the points here, then the subsets you get are a subset containing these 2 points, a subset containing these 3 points. Yeah, so that's the restriction of the set system to a subset of points. In fact, so the condition we will require is that for every y subset of x, the size of it should be S restricted to y, size of S restricted to y, size of y is equal to d, size of y is equal to n. This is O of n to the t. So if you look at a set of n points, the number of possible subsets you can generate is 2 to the n, all possible subsets. But what we are saying is that if you look at any subset of points, the set system is restricted in the sense that the number of possible subsets you can create are only n to the d, a polynomial, much smaller than exponential. And this will turn out to be the crucial property required to construct an epsilon net. Okay. So let's define something called the VC dimension. Some of you may have heard of it because you hear it all over the place in the machine learning theory, and in fact this was defined in the context of machine learning. It's called the Vapnik-Chervonen dimension. Okay. So for a set system, if D is the largest subset of X, no, so let me okay, yeah, so if D is the largest subset of X that can be shattered by S, then the VC dimension of the set system is D. So what is shattered? Shattered means that size of S restricted to y is equal to 2 y, which means you can create all possible subsets of the set y. Right? You could create all possible subsets of small sets smaller than D, but the moment the size of your set y becomes large, then you cannot obtain all possible subsets. Right? In fact, if you have this restriction, this is called the VC dimension of the set system, the size of the largest set that can be shattered. And if the VC dimension is bounded, right? So theorem, if the VC dimension is bounded, then the size of the set system is only polynomial. Okay, again, I'm not going to. Which one? 2 raised to y. This is the largest set that can be shattered. For the largest subset of points for which you can create all possible subsets, by intersecting with the ground, with the subsets. Ah, yes. Yeah. Size of Y is agnostic. So any set, the sets you can shatter are sets of size agnostic. So if your set system has VC dimension D, then the number of subsets you can create are polynomial. Okay, and this condition is sufficient for the entire epsilon net theorem to go through. So again, due to lack of time, let me just state the theorem. This is called the epsilon net theorem. Set systems of VC dimension D have epsilon nets of size d over epsilon log d over epsilon. The important point is that this is independent of n. Okay, I should think I've gone over time, right? Should I take 5 more minutes? Okay, so this is the epsilon net theorem. This is not, this will take some time to prove, so I'm not going to do it. So let's just believe that if you can show that the VC dimension is bounded, then the epsilon, then you have epsilon nets of size 1 over epsilon log. And this also holds, like I said earlier, in the weighted setting. So you can imagine that the points have weights, and a set is large if the total weight of the points is at least epsilon times the weight. Okay. So let me say epsilon net weighted, right? So you have given the set system, and let's say a weight function, and let's say we normalize it so that it's then then a set is large if the weight of S is at least epsilon. Yeah? So the total weight of the points is 1. A set is large if it contains at least total weight of epsilon. It's just the weighted version. Okay, or you can think of replacing each point with as much as a number of as the weight, and then you get the unweighted version. Okay. Then again, the epsilon net theorem holds that if even with weights, if you define large as a set containing at least epsilon weight, then there is an epsilon net of size 1 over epsilon log 1 over epsilon. Okay. Okay, good. So how does all this connect to set cover? Okay, so let's go back to set cover. So you have minimized sigma x sub s subject to sum over all x sub s such that x is in S is at least 1 for all x in X sub S is non-negative. Right. So this is the LP for set cover. Okay. Recall that for general set systems, we have log n approximation algorithm, and that's sort of the best you can do. Now, let X S be a set system with VC dimension D. Okay, so this is not any set system, but it's a set system with bounded VC dimension. Okay, then there exists a log opt approximation for set cover. Now notice that log opt is better than log n, right? So opt could be very small, you might have maybe few sets that cover all the points, but n could be very large. So it's an improvement over the log n approximation for set system with bounded VC dimension. And the proof is the following. Solve the LP. Okay, I don't want to do all that. Okay, so let W be the weight of the LP solution, with the cost of the LP solution. For each x in X, set the weight of X equal to okay. Let me do this as, I apologize, let me do this as hitting set, which is the same thing, right, in the dual set system. Yeah. We want to hit all the sets, all the disks, or all the sets. So what is the, so let's set the weight of X to be X sub V over W, weight of a point V, an element V to be X sub V over W. Okay, right? Since
At point for each xv, say w of v equal to xv by w.
V in X, yeah, sorry. For each element V in X, set its weight to be weight of V over W. Okay. Now, since X is feasible, for the LP, sum over X sub S is at least 1 for all the elements, right? So this implies sigma X sub S divided by W is at least 1 over W, which means that now 5 construct a construct an epsilon net of size 1 over a W net. Now you see that every set has weight at least 1 over W. Therefore, every set is large. Now if you computed a 1 over W net for the set system, then every set contains a point. And so you would have a hitting set, right? And by the Epsilon Net Theorem, there exists an epsilon net of size 1 over epsilon, so d times log 1 over x. So assume that d is constant, log d over epsilon, and this is w log w, where w was just log opt, was just opt of the LP, but the optimal solution for the LP is at most the optimal solution for the integer program. Therefore, okay. So the epsilon net is just a random sample, each element chosen with certain probability. But to get an approximation, you solve the linear program to get the optimal solution for the linear program. Then you know the value of epsilon, for which you need an epsilon net. Just invoke the epsilon net sampler, which just samples points with some probability, and that becomes a hitting set, and the cost of the hitting set is at most opt times log opt, and therefore it's a log opt approximation for the hitting set problem. So via epsilon nets and VC dimension, you can get better approximations for geometric settings. Now I rushed through a whole lot of things about VC dimension, which takes a lot of time to digest. So what I'm going to do is I'll send you notes now for the earlier lecture as well as today's lecture, and that has lots of examples of set systems with these small VC dimension, etc., and to get a better idea.